Okay, welcome to the last day. What is today's date, by the way?
12.
Today's the 12th. All right. You know, I worked for years in public schools, and we always get out. The 23rd is always the last day for the break. And then we come back on the 2nd of January. It's always very short. It's like a week. 10 days tops. 10 days. So this is lovely. 3 weeks. Lovely. So that's 15 days plus 3 weekends. So that's 15 plus 6. It's 21 days. It's really cool. A little bit better than 10, don't you think? Okay, so let's begin. Now, when you take biology and middle school science, you're going to inevitably study the atom. You're going to inevitably study chemistry. Yesterday, I did the first video relative to bonding. And we said that this unit, binary unit, is going to be 2 chapters, 7 and 8. Now, there are things in this chapter. Chapter 7 is ionic bonding and metallic bonding. Correct? Okay. Ionic bonding is the transfer of electrons, and metallic bonding is anybody?
The sea of electrons?
The physical, it's like a sea of electrons and protons, and there are physical forces which hold them together in tight formation, correct? Based on their electronic natures. Sounds good? Yeah. We'll get more into that a little bit later. Okay, oh, we have a guest. We had a law student. Poor smile. We had a law student. Okay, you can just go that way. Okay, thank you. Kamal's bringing him in. He's in a wheelchair. He looks very sad. He's approximately, how many minutes late is he? 10, approximately? Approximately 10 minutes late, but we'll forgive him because he's in a chair.
Okay, so I have a knee injury and I'm not.
Well, we don't, yeah, I understand that, but you've been riding that train for about a month.
Me?
All right, let's begin, shall we? Lizzie, I forgive you.
Thank you.
You're welcome. Okay, let's begin. Again, now, he's parallel parking. This is very exciting. I feel like I'm in the middle of the interstate watching a car out of control.
You're supposed to roll him down.
Yeah, this is, now let's see if he can do this. Now do both, oh, he's got it, man, I'm telling you, the guy's good. The guy's good. Now, if you needed a license to ride a wheelchair, and part of it was getting behind 2 tables, between 2 tables, like parallel parking with cars, you would pass like with flying colors. You could actually teach that skill, I think. You're that good. We simply call you, instead of Ishmael, we'll call you the professor. Okay? Good. Excellent. So, now, then covalent bonding is a sharing of electrons. Covalent bonding is, a whole chapter is for covalent bonding. A chapter called Chapter 8, covalent bonding, sharing of electrons. In today's lesson, what I really want to do is talk about covalent bonding. That's really what I want to do. Okay? Talk about covalent bonding. And covalent bonding is when you have 2 bonds. This is 2.4 and this is 2.1. Is that correct? Yes or no? What is that? Could you look that up in your books, please? You know what? Let's take a slightly better example. That's actually a good example. Let's take a better one, okay? Okay, is that about correct? Yes? All right. Turn my bells off on my phone. What was life without phones? I could tell you, actually. I grew up without a phone. I got detention in 8th grade because I was listening to a transistor radio with an earphone going up my shirt, around my ear. I was listening to a Mets game, New York Mets baseball, World Series, 1969, Baltimore Orioles, Game 3.
You know the exact same.
Yeah, it was, middle innings. All right, now, chlorine is going to dominate that bond because it has a larger electronegativity and you're creating a dipole. The dipole is in the shift of the cloud, correct? Now, as opposed to this kind of bond, where you have no shift because you have an equal distribution of charge, so you have zero shift. The shift indicates a dipole. It indicates polarity. Nonpolar, polar. A bond is either polar or nonpolar, correct? Now, let's look at this. What's the electronegativity of carbon? Did you look that up, anybody? Go to the table in chapter 6 on electronegativities and look up the electronegativity for carbon. Okay? Yes. 2.5. And what's hydrogen?
2.1.
2.1. So you could consider why would hydrogen be so high electronegative and it's on the left side of the table? Why would that be true? Why would hydrogen have such a strong tendency to attract bonded electrons relative to carbon, which is really fairly close to fluorine? Why would that be?
Maybe because of hydrogen gains another electron.
Well, if you're talking about the bonding site and covalent bonding, you're not talking about the transfer of charge and a new valence state. What's the valence state of carbon if it bonds covalently? It's still the same. 2, right? The second shell, right? So the bonding site, where the electron is going that's sharing, is a certain distance from the nucleus, is 2 shells out, correct? Where hydrogen is where? It's only 1 shell. It's very close to the nucleus, isn't it? Look at the ionization energy of helium. It's through the roof. That second electron is held very tightly in that particular configuration. So when you have 2 electrons bound in the first shell, such as helium, and hydrogen, which wants to be like its nearest noble gas, helium, in the bonding process, that electron is attracted to a much greater extent than carbon as a result of that. That's a serious oversimplification, but it still works. Okay? So you have these 4 dipoles, and you know what? I may have even said in the past that the dipole is going the other way, is going towards carbon, whatever I said. It's irrelevant. What is relevant in terms of the nature of methane you know it by its common name, natural gas, methane. Well, most of you, if you live in an apartment here in the city, you have natural gas. If you're, I don't know, in other places, you have propane. El Reef has propane. So this is methane, and methane has polar bonds. It has 4 polar bonds, but its molecule is nonpolar because it cancels out. Now, part of the lesson today is going to be talking about molecular geometry. And the molecular geometry will take these 4 opposing dipoles and balance them out. In 2 dimensions, you can see intuitively that they're going to balance out, correct? Well, if you have no net dipole, you have no polarity. You can only have polarity if you have a net dipole. For instance, let's say I took one of these hydrogens off and I put chlorine. This dipole, the difference here, is different than the difference here. Correct? It's different. It's a little different. It's not the same dipole. So this is going to be polar. Because you have a difference in dipole. You have a net dipole. Correct? You see that? If I put fluorine here, it would be even more polar. Correct? So you have polar bonds, nonpolar bonds. You have polar molecules, nonpolar molecules. It all has to do with dipoles. A polar bond has a dipole. A nonpolar molecule has all the dipoles balanced. Correct? Now, the next thing we want to talk about, that was a bit of a review from yesterday, would you agree, Genevieve? Yeah. Would be, whoa, watch the sneakers. Would be molecular geometry. Molecular geometry has two things. It has a rather nice set of very consistent rules with very few exceptions. And it makes sense. It makes sense in terms of the geometry and charges and your understanding, your intuitive understanding of what a charge is, and two charges repel, two like charges will repel, correct? Those sorts of things, correct? Okay. So I'm going to give you a set of rules while I do this, all right? I'm not going to write them on the board. You can write them yourself, and then if you want them repeated, look at the video twice. Okay? Easy? Okay. We're going to do a series of molecules, right? Now this is in the covalent bonding chapter, so things are going to range from polar molecules, very polar molecules, to very nonpolar molecules in terms of geometry. Okay? Clear? All right. Let's start off with a very basic molecule, and it's very common, you know of it. And what I'm going to do is, you have to do this from the formula. So let's say I have H2O, okay? 2 H's and 1 O. Anybody know what that compound is? Water. What do you think the central atom is going to be, hydrogen or oxygen?
Oxygen.
Oxygen, okay. So that's the basic combination. Would you say that's correct? We don't know anything about its geometry yet, do we? We just are working from scratch. It's okay to put this in a linear line form, all right? The next thing you do is you count the valences. Now that's just that's like chemistry speak. What does it mean, the valence? What is the valence of hydrogen? What is the valence of oxygen? Yes?
How many outer electrons it has?
You are brilliant. Yes. It's the valence is simply another way of saying the number of valence electrons. So what's the valence of hydrogen? 1. What's the valence of oxygen? 6. I know, you had a little bit of a... If you go like this, you sometimes can reboot the computer upstairs. Okay? All right. So what's the total valence of H2O?
8.
Very good. So the first thing you do is you write the total valence. All right? So you want to write that down. Total valence. I'm going to use the word valence a lot, so I'm going to use the letter V for valence. Is that okay? All right. So the total valence is 8. Number 2. You want to subtract from the valence the total number of bonded electrons. All right? Total number of bonded electrons. How many, what is the total number of bonded electrons? There's two electrons for every bond. 4. 2 plus 2 is 4, okay? You're left with 4 electrons, okay? The next thing you do is you complete, listen very carefully, let me say that again. The next thing you do is you complete the valence of the outer atoms. O is outer. I'm going to use outer a lot. O is outer. So, does hydrogen have any outer electrons? No, right? Doesn't have any. It has one electron that's in the bond, right? So, there are no outer electrons, right? So, 4 minus 0 is 4. Is that on there? Can't see. Where's my glasses? There they are. Yes. Okay. All right. So now, what do you do with the remaining electrons? What do you do with the remaining electrons? You put them around the central atom. Right? Now, another rule, rule 4. Right? Central atom. Right? A. Non-metal. Okay? Non-metal. Right? Number of electrons greater than or equal to 8. Greater than or equal to 8. Does that make sense? Did I rewrite that? Make it in red. So how many does oxygen have? 2, 4, 6, 8. Who do we appreciate? Right? Correct? So does that satisfy that rule? Are we okay? Yes? Excellent. All right, now we have to talk about the geometry. Well, you don't have the list yet that I'm going to actually have you memorize. Terrible, I'm a rotten person, but I want you to do that. It's one of the few things I say to you. Memorize. Okay? So you'll look at your sheet and you'll say, well, let's see. Let's see. A central atom, 2 bonded pairs, and 1 non-bonded pair. Okay? So you'll look at your sheet and you'll say, I got to find 2 bonded pairs, 2 non-bonded pairs. So it's going to look like this. You have one that looks like this. There's a circle that represents the central atom, and then bonded, right? Where it's a straight line is bonded, and then you'll look for it like this, like that. Isn't that it? 2 bonded and a non-bonded? You see this? Approximately 109 degrees. Yes? Approximately? Yes? Yes? Right? Okay. This is called, what's with the squeaking? Somebody's squeaking. Can somebody stop with their sneakers? They never wear sneakers. They always have to wear regular shoes. They don't know how to operate sneakers in this class. Okay? Before you wear sneakers again, you must go to the National Sneaker Testing Center. Okay? Yes, and you must show me your certificate, or you can't wear sneakers. Excuse me? Thank you very much, Lizzie. I appreciate your comments. Excellent. Superman lives forever.
Supergirl.
My apologies, Supergirl. Very good. Excellent. Now, so you have what? It says the type of geometry says right here. It says bent or angular. You'll see both. That's the geometry. There's an angle there. Yes, 180 degrees is an angle, but they say angular or bent geometry. Easy? Yes? Okay. Let's go through. We're going to erase all this, and we're going to go through another example. Okay? Let's go through a really super duper funky example. Okay? Right? Lauren, you know what I'm talking about, right? Okay, here we go. You ready? You ready? Okay. Very funky. Yes, the heavier noble gases can form compounds. They can form compounds. The influence of the nucleus and the stability of the outer electrons becomes a little crazy when the atom becomes very large. So xenon can form compounds. Xenon difluoride, using the Greek system, xenon, no mono, di, 2, fluoride. Clear? Okay, so what's the total valence? Very quickly now. You can do it. You can do it. What's the total valence? You're having a problem counting today. Simple addition. What's the valence for xenon? It's a noble gas, so there's going to be 8. Good. What is the valence for each fluorine? 7. Now, what is 7 plus 7 plus 8? They're taking out their calculators. What is it? 22. Right? You got it? That's the man in the wheelchair. Excellent. Excellent. Okay. Clear? So that's 22. Now, we've got to subtract off the number of bonds. What do you think is going to be the central atom? Xenon or fluorine?
Xenon.
Yeah, it's probably the one with the fewer number of atoms involved. There are some laws that we will talk about, some rules that I'm kind of ignoring right now. I want to just get through a few of these. So it would be xenon, fluorine, fluorine. Okay? Yes? All right? You with me? Okay. Now, what's the total number of bonds? What's the total number of electrons that are in bonds? 4. So you subtract off 4. This is bonds. And that leaves...
18.
That leaves what?
18.
18. Let's move this over so we can do our math. So it's going to be Xe, fluorine, fluorine. Okay, so we have 18. Right? Now we're going to subtract off, yes?
How do we know it's 4 electrons?
Excuse me? I can't hear you.
How do we know it's 4 electrons? How?
Because there's 2 bonds. 2 plus 2 is 4. Yeah, what were you thinking?
I just didn't know like where you get 4 from.
That's okay. You get it now? Excellent. All right, now. I say it a lot, excellent, don't I?
Yeah.
Yeah, I'm sorry. My apologies.
I didn't worry. I didn't.
Thank you, Lizzie. She just wants me to mention her name on camera.
What?
Nothing. So now, so there's 4, so there's 18 now, correct? Now, complete the valence. What does that mean? So you want to subtract off, and you want to complete valence. What's the valence of fluorine? 7, right? Correct? Okay, this one is from fluorine. How many more go around it? Okay, so how many does it have? It has this one is from fluorine. Does it have, how many does it have here?
One.
No. This one is from fluorine, but this one is from xenon. So how many does fluorine have right now? Two, correct? How many does it need? How many extra does it need?
6.
6, because it needs what?
8.
8. Hydrogen only needed 1 because it had 1, so it needed 2 because it was going to be like helium, correct? So what does fluorine, what total number of electrons does it have? It's going to have 7. It has 1 from xenon, that makes 8, right? So it has 1 from xenon, 1 from fluorine, and then how many more do you have to put around? 6. Right? Around both. You'll get so you don't really have to do this. What are these called that I'm doing, sort of? Like, what is this? The dots, what does that mean? Starts with an L. World champions in baseball. What comes after a sentence? Lewis dot diagrams. St. Louis. Dot comes after a sentence. Yeah, the Americans should hang their heads in shame that they don't know that the World Series champions are the St. Louis Cardinals. Aren't they? Am I losing it? Yes, of course they are. Yeah, I knew that. All right. So, how many, when you complete the valence, how many total valence electrons did you put in? 12. 6 and 6, right? You get it? So what's 6 and 6? 12. So what's 18 minus 12? 6. Oh, by the way, I'll give you a hint. The total valence here is always going to be an even number. Always. Okay? Always. Yeah? Okay. So, now what? What do I do with the 6 electrons? I just don't get rid of them. I don't give them away. Electrons here! Programs here! Electrons here! Buy some electrons here! What do I do with them? Lauren? What do I do with them? I share them. No.
Give them away.
No. I put them around the central atom. Who said that? Genevieve? Excellent. I put them around the central atom. So how many pairs of electrons do I have around the central atom? How many? I have how many? How many do I have? I have what? I have 3 pairs, okay? Does anybody have a pencil? I need 3 pencils and 2 pens. Excuse me. 3 pencils. The pencils are going to be the non-bonded electrons. I need 2 pens. Yeah, sorry, I'm not going to kill it. I need another pen. There it is. Look at this. The pens are the bonded electrons. The pencils are the non-bonded electrons. Correct? What is the geometry relative to the bonded electrons in the central atom? Is it, shall I give you some choices? Does it make a square? Does it make a triangle? Does it make a straight line? This pen going through the central atom to this pen, what's the angle? It's 180. What's another word for 180 if you were describing the angle? It's a straight line. What else? It's an L word. What's an L word that describes a straight line?
Linear.
Who said that? That was a team effort? Excellent. Linear. So this is linear. Difficult to draw linear on the board. Difficult to draw linear on the board, but it's kind of like this. It's kind of like you have a thing there, and then you have something like that. Okay, where you have three unbonded pairs, right, 120 degrees apart. Okay, and then you have this 90. The 180 degree relative to the bonded pairs, which is linear, okay? So then you would say that it is linear. You say linear. Linear, okay? I'm going to stop the tape. We'll take a break. I have to advise some students about their behavior. Okay, so excellent. So we'll be right back, okay? And while I'm waiting, we can maybe do another one. Okay, shall I erase this one? And I'm going to let you try to do this. Okay, I'm going to end this with this, and you try to do this yourself. You ready? Okay, the hint is very funky. Okay? Be right back.